It's been a while since I made any updates to the low-res library. You know, real life and all. I wanted to revisit the scrolling platformer demo I was working on and decided to spend some time optimizing the library in order to give the game a little more overhead during an active video. Time spent away and fresh eyes garnered me a few percent speed up. A lot of work for a little gain, but there is enough time for the game to include more graphical elements. I had to spend effort profiling the library and decided to write up the process one might do for a game. A video seemed more appropriate given the visual nature of the low-res library. So, profiling the low-res library and games using it. This is a simple and effective approach. Now, the CGA allows real-time update of the border color. So we use this color to identify sections of code in the library. This will create a nice bar graph because the program loop is synchronized to the vertical blank, actually the end of active video. And here we are looking at one of the early demo programs used to debug simultaneous scrolling, tile updates, and sprite updates. The frantically pulsing square in the middle is a tile image being repeatedly changed. The yellow sprite is just bouncing around and is of lower priority than the red sprite, so it will move behind the red sprite. I have modified this version of the demo to allow pausing, so let's take a look at that. Here we come, and there you can see our yellow sprite is actually moving behind the stationary red sprite. Now, this computer is a Compaq Desk Pro 8086 running at just over 7 megahertz and is able to complete its processing every frame. We can see the border colors displaying where time is being spent in the library and the demo. Looking at our border colors, the reddish pink is the critical rendering code that has to happen during inactive video to avoid CGA snow and image tearing. You see it begin just after the last visible scan line here at the bottom. Occasionally, you will see red at the top of the screen during complex screen updates. As long as the red doesn't bleed into the active part of the screen, starting with the top scan line, everything is okay. Following the red border is a black section. This represents time spent in the game logic. Now, this demo is quite simple, so most of the time is spent looking for a key press using the KB hit routine, which is surprisingly slow. Then we come to the blue section. This is the setup code inside the low-res library, calculating intersections and pre-rendering all the image buffers. Following the blue is the green section. This is just idle time, waiting for the end of active video. And it starts all over again, drawing the pre-rendered buffers in the red section. Now, what happens when we slow the machine down to 4.77 megahertz? Now, this computer is still slightly faster than a 4.77 megahertz 8088, being an 8086. But you can see the demo doesn't complete its loop during a single video frame. The frame rate staggers and the border bars flicker. Now, what are some methods to address this frame complexity? Well, first, let's define frame complexity. Vertical and horizontal scrolling When you scroll, the low-res library must fill in the newly scrolled in rows and columns from the tile map. Newly visible sprites during the scrolling must be rendered as they appear. So let's take a look at that. So right here we see our red sprite becoming visible as it scrolls into view. Also, updated tiles must be drawn if they're visible. Moving sprites, our little yellow guy here, must be erased from the previous location and drawn at the new location. Now, the low-res library will make an optimization and just include more background to erase the previous position if it's moved just a small amount. This demo does all of this every frame, thus overwhelming a 4.77 megahertz x86. So, here are some ideas to reduce the CPU load. First, you can reduce the size of the sprites. The sprites in this demo are actually about as large as you'd ever want to go. Don't overlap the sprites if possible. This adds complexity to the pre-rendered buffers. Here you'll see we have to render our red sprite above our yellow sprite, even though the yellow one is the guy moving underneath. So that adds quite a bit of complexity to the intersections and rendered buffers. Another thing you can do is actually reduce the number of on-screen sprites. If some of the sprites are mostly static, you can convert those into a tile. Tiles come for free and can be updated easily, as you can see with our square. And then one of the other things, last things you can do, is interleave the updates. Not everything may need to be drawn every frame, thus reducing the per frame load on the CPU. So for instance, we may not have to scroll and update our tile during the same frame. It might be possible to do a scroll in one frame and a tile update in another frame. So let's take a look at some of these options and what we can do to get our timing back on a 4.77 megahertz CPU. Now what we've done here is actually shrink the size of our on-screen sprite. We still have the same number of sprites and everything else is now equal, except our sprites are slightly smaller. Now you can see that for the most part, we're actually making timing. It's only when things get a little complex that we're not making our timing. Again, seeing complexity where our sprites overlap, as well as when our sprites start to scroll into view, do we still have too much complexity in our scene? So let's try another approach to reducing the CPU load by interleaving some of the operations between frames. Now you can see that we've made some changes. And the big one is that we've interleaved the moving of our yellow sprite and the updating of our tile to be in alternate frames. So this effectively halves the frame rate of our sprite moving and scrolling and our tile update. The question you'd have to ask yourself is that adequate? Is that okay to have the movements at that speed versus at the higher speed? And maybe you'd have to make a different approach to getting your rendering load reduced. So even in this case, you can actually spot one little section right as our sprites overlap. right there that we actually still exceed just by a smidge our rendering interval, and we actually do skip a couple frames. So when we watch our blue line come all the way down into our inactive video, we miss our opportunity to get the frame rendered. So this is still going to require probably a little more effort trying to reduce the load. And like one of the easy ones would be to do is to just not have sprites big like that overlap each other. So if we move our yellow sprite slightly off to the side, it won't step on top of our red sprite, and see if we now completely meet our timing requirements. Now we've moved our yellow sprite away from our red sprite, and now you can see that we have a great deal of overhead. Look how much green we have available to us for our game to become more complex, more rendering to occur. So this is the challenge you will have with this low res mode and library, is trying to find those instances where the CPU becomes overloaded and avoid them, and find different strategies to work around those cases. So for this case, we might even be able to revert back to our full 60 frames a second scrolling demo. So let's try that and see what happens. Well, unfortunately, it looks like we still have just too much load as our red sprite scrolls into view to not be able to update it at the full 60 hertz like we originally had. So with our 4.77 megahertz CPU, we're definitely going to have to find a couple of strategies in order to work around the CPU load. But this gives you a couple options, and the procedure, the methodology you would go through in order to identify what you can do for these given challenges as you develop for this low-res graphics library. Now, as a final test, I thought, well, let's try disabling the update of that tile, thus reducing our load even more and seeing what we find on the screen. And now we see we have a great deal of green. As we scroll that red sprite into view, we do get a higher load on our rendering because that's what we have to do to draw that visible sprite. But we are now well within our margin to pull off this kind of a frame rate with those screen elements. This tile normally wouldn't be getting updated very often. Usually you would make an update as you would grab an item and change its state. So relatively rare would you really be updating the tiles like that. So this is probably a more realistic view of what you would have on a game. So I thought that's the kind of the way we'd wrap this one up. We did have to simplify our CPU load and graphics load quite a bit to pull off the kind of frame rate we were hoping to get. But I think that's the challenge of using this low-res video mode and the library. Hope somebody does take me up on trying to write their own game using this library. So, thank you for watching.